Welcome to the Unit 3 Section 8 video on solving quadratic inequalities. So throughout the course of this unit, we've talked about different ways that we can solve quadratic equations. Now we're just going to take it a step up and talk about how to solve quadratic inequalities. So remember back to the last unit, we did talk a little bit about quadratic inequality. We talked about how we solve a quadratic inequality in two variables by graphing. Okay, and so that was done by simply graphing our inequality. So here, for example, we have y is greater than x squared minus 6x plus 5. So we would graph that, and of course we would have a dashed line because there's no equals to portion, and we would shade above the parabola since it's greater than. So everything in this shaded area would be part of your solution. And we would not include anything along the dashed line as part of the solution because there's no equals to part. So if this were solid, it would include the boundary, but since it's dashed, it does not include the boundary. And again, that was in two variables. Well, now let's talk about what if we have one variable. So if we have a quadratic inequality in one variable, for example, x squared minus 6x plus 5 is greater than 0, the y goes away because we have some value for y now, which is 0. This is a quadratic equation or a quadratic inequality in one variable. So let's consider the graph of the related quadratic equation, which would be y equals x squared minus 6x plus 5. If you have this graph of the function here, and we wanted to find out where x squared minus 6x plus 5 is greater than 0, we would simply look to see where it's 0, and then where is it greater than 0. So everywhere that this graph is greater than 0 would be above the x-axis. So what we would have is an interval. And that interval is negative infinity to 1, union with 5 to infinity. Okay, so basically everywhere where it's not negative is where it's positive or where it's greater than 0. And so that's how we find it graphically. Well, we don't have to look at just a graph to be able to do this. We can do this algebraically. So let's talk about how we do that. To solve a quadratic inequality algebraically, recall that the x-intercepts determine the intervals where a function is positive or negative. Okay, so as you saw in that previous graph, where we stopped being positive, we started being negative, and then where we stopped being negative, we started being positive. And that point where we switched over was our x-intercepts. So if we want to find our x-intercepts algebraically, we can take our inequality and use the related equation. So basically we take our inequality and replace it with an equal sign. And then we solve normally to find out what our x-intercepts are, or our roots, or our zeros, or our solutions. Remember, those are all the same words for our x-intercepts. So when we do that math, we're able to factor it and we get x equals 1 and 5. Now, rather than graphing the entire function, let's simply consider these points on the x-axis or a number line. So I plotted these points on a number line here. And when I did, we have 1 and 5, and I put open circles on both of those just to remind me that we are not including them because we have a greater than, not a greater than, and equal to. So we want to find a test value that is in the other portions of this number line around our x-intercepts. So we start with a test value that's less than 1. 0 is a good choice for that. And when we put 0 into our inequality that we're presented with, we find that 5 is greater than 0. Since that's a true statement, we put a check on that portion of the number line because it will be included as part of our solution. Then we move on to a number between 1 and 5. In this case, we use 3. When we put 3 into our inequality, we get negative 4 is greater than 0, which is false. So we put an X on that part of the number line so that we know that is not going to be included as part of our solution. And then finally, we find a number that's greater than 5. So we use 10 here as our test value, plug that into our inequality, and we find that 45 is greater than 0. That's true. So we put a check there. and that gives us the portions of our number line that will be included as part of the final solution. And so since we found what our final solution is, you're able to take that and plot it on the number line, as I did here. You're able to put it into set notation, which you can use your number line to find that. We have x is less than 1 or x is greater than 5. And then in interval notation, it's negative infinity to 1, union with 5 to infinity. So that's basically the whole concept of how you go about solving algebraically. So for the rest of this, we're just going to do some examples to get you comfortable with the process of determining what the solution set is. So let's begin with this example. We want to solve x squared minus 4x plus 1 is greater than 6 algebraically, and then we'll express the solution on a number line in set notation and in interval notation. So when we do this, first thing we have to do is set our related equation. So simply just take the greater than sign, replace it with an equals, because we're interested in finding out what our x-intercepts are. So to do that, we're going to subtract 6 from each side to get it completely in standard form. And so that gives us minus 5 equals 0. Okay, now we're going to look and see if we can factor this. If we can find two numbers that multiply to give us negative 5 and add to give us negative 4. And once you think about it, those numbers are 1 and negative 5. So our solutions are going to be negative 1 and positive 5. So now that we have our x-intercepts, we're going to draw a number line. And we're going to plot our x-intercepts on there. Now, we're using greater than, so we're going to put an open dot on each part, just to remind us. And then we're going to test each part of the number line between our x-intercepts. So for the first test value, let's use negative 5. So we're going to put that back into our original inequality that's in the original problem. Because negative 5 is less than negative 1. We're testing this part of the number line. Okay, so when we do this, we end up, when you do the math, with 46 is greater than 6. So that is true. Since that's true, this part of the number line gets to be included. The next number we're going to test is 0 because that's between negative 1 and 5. And when you do that math, which is very simple, you get 1 is greater than 6. That's not true, so we're going to put an x there. And then finally, let's use 10, because that's greater than 5, and 10 is a fairly easy number to use. And when you do this math, you end up with 61 is greater than 6, and that is a true statement, so that does get included. All right, so now that we have the parts that are included, now we just come down to our solution number line, and we're going to put negative 1 and 5. They're both going to have open dots. And then we're going to have a line going from negative 1 to the left. And we'll have a line going from positive 5 to the right. Now we can look at our number line and figure out what our set notation answer is going to be. It's going to be x such that x is less than negative 1, or x is greater than 5. And in interval notation, you'll have negative infinity to negative 1, union with 5 to infinity. And that would be your answer for this problem. In fact, that's 3 different ways of expressing your answer for this problem. All right, let's move on to example 2. We're going to solve this problem algebraically. Again, we're going to start with the related equation. We'll subtract 11 from each side, and when we do, we get x squared minus x minus 6 equals 0. And then we're going to factor this. When we do, we get x plus 2 times x minus 3 is equal to 0. So that means x is going to be either negative 2 or 3. So now we come down here and we do our test line. We got negative 2 here, we've got 3 here. And they both have open dots on them. So now we go to our original inequality and we plug in some test points. So the first test value I'm going to use is negative 5. So we'll have negative 5 squared minus negative 5 plus 5 is less than 11. And when we do the math, we get 35 is less than 11. And that's not true. So we're going to put an X there. So let's move on to our next test point. 0 is the obvious one to go with here. Whenever you can use 0, use 0. And that gives us 5 is less than 11. And that's true. So we're going to put a check on that part. And then finally, let's just use 10. 10 is greater than 3. 10 is fairly easy to work with. And when you do that math, you get 100 minus 10, which is 90, plus 5. That's 95 is less than 11, I should say. And that's not true. So we're going to put an X there. So now we have everything we need to write down our final solution. We've got negative 2 here. We have 3 here. Both are going to contain open dots. And we are going to be shading everything in between. In set notation, we can write this all in one go. X such that negative 2 is less than x, which is less than 3. And then in interval notation is simply negative 2 to 3. So you'll notice that these problems are fairly quick to do as long as you know what you're doing. And there's nothing extremely hard about it either. All right, let's go on to example 3. So again, we're going to start with the related equation for the inequality. And we're going to get this into standard form equals 0. So we'll have plus 5 there equals 0. And now we're going to factor. And when we factor this, we get x minus 1 times x minus 5. And so therefore x is either 1 or 5. So now we're going to do our test number line. And so we've got 1 here, and we've got 5 here. So now we're going to get some test values. So let's give our test values a try. Well, first of all, this is going to be less than or equal to, so we're going to have a solid dot here at 1, and we're going to have a solid dot at 5. Okay, so now let's test out values. We'll start off with 0 because that's less than 1. So we got 0 squared minus 6 times 0 plus 8 is less than or equal to 3. And when you do that math, you end up with 8 is less than or equal to 3. That is not true, so we're going to put an X on that. And that X is also going to go over here on the number line. Now let's check 3. That's between 1 and 5. So we've got 3 squared minus 6 times 3 plus 8 is less than or equal to 3. And when you do that math, you're going to get negative 1 is less than or equal to 3. And that's true. So on the number line, we're going to put a check there. And then finally, we're going to try a number bigger than 5. Let's go with 10 again. 10 squared minus 6 times 10 plus 8 is less than or equal to 3. And when you do that math, you end up with 48 is less than or equal to 3. And that is false, so we put an X there and on our number line. So now we have everything we need to do the final answer for this. So we have the numbers 1 and 5, and we have a solid dot at 1 because we're including it. Same thing for 5. And we have everything between the 1 and the 5 as part of our solution. So now we have the number line. Set notation is fairly simple because all we have to do is x such that 1 is less than or equal to x, which is less than or equal to 5. And in interval notation, we have 1 to 5 all inclusive, which means we use brackets. And I should say -1 here. Actually, no, it is 1. It is 1. Okay, so that is the solution to that. Let's move on to the next example. So here we're going to solve this inequality algebraically. So let's begin by taking our inequality and writing down the related equation. And then we're going to get everything to one side, so we have standard form. And now we're going to factor this. And when you factor it, two numbers that multiply to give you -11, add to give you 10. That's 11 and -1. And so our x is going to be either -11 or +1. Now that we have our x-intercepts, we're going to do our test graph. We've got -11 here, we've got 1 here, and we know both are going to be included, so we'll go ahead and put that on our test line to remind us when we get to our final solution. And now we need a number that's less than -11. Well, how about -15? So we'll do -15 squared plus 10 times -15 plus 1 is greater than or equal to 12. When you do that math on the left-hand side, you get 76 is greater than or equal to 12. And that is a true statement. So we're going to put a check on that part. Now our next test value will be 0, our tried and true. And when you do that, you get 1 is greater than or equal to 12, which is not true. So an X on that part of the line. And then finally, a number that's greater than 1, let's use 10. You can use 2, you can use 5. I just choose to use 10 here. And then when you do that, you're going to end up with 201 is greater than or equal to 12. And that's true. So we come down here and we graph our final solution. We have -11 and we have 1, and we know that we are going to have a solid dot at both of those points. And we are going to be shading everything to the left of -11 and everything to the right of 1. So our set notation, we have x such that x is less than -11, or less than or equal to, I should say, or x is greater than or equal to 1. And then in interval notation, we have -infinity to -11, bracket, union with another bracket, 1 to infinity. And there are your 3 answers. All right, moving on to example 5. Again, we're going to start off with the related equation to our inequality. We'll move the 28 over to the other side. And that gives us negative 16 here. And now we're going to factor this. Now factoring this is going to require some factoring by grouping. We need two numbers that multiply to give us negative 48, because that's 16 times 3, or negative 16 times 3. Two numbers that multiply to give us negative 48 and add to give us 22. And that would be 24 and negative 2. So we're going to split up our middle term into 24x minus 2x. Then you have the minus 16 here. And now we can factor by grouping. We can pull a 3x out here. That leaves an x plus 8. We know we want an x plus 8 over here. And the way we achieve that is by pulling out a negative 2. And so we have x plus 8 times 3x minus 2. So for the x plus 8, we know that our solution here is going to be negative 8. And then our solution for the 3x minus 2 is going to be 2/3. So the 2/3 should not dissuade you from continuing into this problem, because we're really not going to do much with the 2/3 other than sit it on a number line. So we've got negative 8 here and we've got 2/3 here. And we know that both of these are going to be open dots, okay? So now let's do our test points as we always have. Let's use negative 9 for a test value in this first one. So we've got 3 times negative 9 squared plus 22 times negative 9 plus 12 is greater than 28. When you do the math on the left-hand side, you get 57 is greater than 28. And of course, that is a true statement. So this part of the number line checks out. Now we'll use 0. 3 times 0 squared plus 22 times 0. All of that's 0 so far. We're just left with 12 is greater than 28. And 12 is greater than 28 is a false statement. So we put an X there. And then finally, what's a number bigger than 2/3 that we can use? Well, how about 1? 1's easy enough to work with. So when we use 1, the left-hand side becomes 37. 37 is greater than 28. It sure is. And so we've got a check there. So now we are going to write down our final answer. So we have open dots here and here. Let me draw those a little bit better. And the values that go with these open dots are negative 8 and 2/3. And we have solutions going to the left of negative 8. We have solutions going to the right of 2/3. In set notation, we have x such that x is less than negative 8 or x is greater than 2/3. And in interval notation, we have negative infinity to negative 8 union with 2/3 to infinity. And those are our three versions of our solution. All right, moving on to the next example. We've got 2x squared minus 3x minus 32 is less than 3. We're going to start off with our related equation. And that would mean we would actually use an equal sign there. Okay, let's solve this one by grouping. Well, first of all, let's get this 3 over to the other side. And when we do, we have minus 35. So we need two numbers that multiply to give us negative 70 and add to give us negative 3. and that would be 7 and negative 10. So we have 2x squared plus 7x minus 10x minus 35 equals 0. All right, what can we pull out of the first two terms? Well, all we can pull out is an x, so that leaves us with 2x plus 7. We know we want a 2x plus 7 out on the other one, and to achieve that, we're going to do minus 5. And so we end up with 2x plus 7 times x minus 5 equals 0. So now that we have that factored out, we can find our x values. X is going to be negative 7/2 or positive 5. So those are our two values on our number line. We got negative 7/2 and we've got 5. And since we're less than, there's no equals to part, they're both going to be open dots. All right, let's start with our test values. Negative 5 is less than negative 7/2, so let's use that as a test value. So when you do the math on the left-hand side, you end up with 33 is less than 3. That's not true, so we're going to put an x there. Our next test value obviously is going to be 0, so we got 2 times 0 squared minus 3 times 0 minus 32 is less than 3. Well, negative 32 is indeed less than 3, so that checks out, so that part of the number line's good. And now we need a number that's bigger than 5. Let's go with 10. 2 times 10 squared minus 3 times 10 minus 32 is less than 3. When you do the math on the left-hand side, you end up with 138. And that most certainly is not less than 3. So we put an x there and on our number line. So now, all we have left to do is write our answer. We've got negative 7/2 and we've got 5. So we know both of these are going to be open dots. And we're doing all the points that are in between, because that's the part of the number line that's checked. So in set notation, this is going to be x such that negative 7/2 is less than x, which is less than 5. And in interval notation, it's going to be negative 7/2 to 5. And those would be your answers. On to example 7. We've got 2x squared minus 3. We're going to set that equal to 5x. So now we're going to move our 5x to the other side. And we'll put it in the middle so it's in standard form. So we've got 2x squared minus 5x minus 3 equals 0. Well, let's see. We need two numbers that multiply to give us negative 6 and add to give us negative 5. Well, that would be 1 and negative 6. So we've got 2x squared plus x minus 6x minus 3 equals 0. So what can we factor out of the first two terms? Well, x is all you can pull out. And we're left with 2x plus 1. We know we needed 2x plus 1 here. And to achieve that, we're going to pull out a negative 3. And so this factors into 2x plus 1 times x minus 3, and that's equal to 0. So our values for x are going to be either negative 1/2 or 3. So we pull out our test line. We've got negative 1/2 here. We've got 3 here, and we've got less than or equal to, so we know we're going to have solid dots on both of those points. And now we just got to do our test values. So a number that's less than negative 1/2 is negative 1. So let's do 2 times negative 1 squared minus 3 is less than or equal to 5 times negative 1. Well, when you do that, on the left-hand side you get -1. On the right-hand side, you're going to end up with -5. And that is false, because -1 is actually larger than -5. So we're going to put an x there, and we'll move on to 0 as our next test point. 2 times 0 squared minus 3 is less than or equal to 5 times 0. So you have -3 is less than or equal to 0. Well, that checks out. And now we need a number that's bigger than 3. How about we go with 5? 2 times 5 squared minus 3 is less than or equal to 5 times 5. On the left-hand side, you end up with 47. On the right-hand side, you end up with 25. 47 is not less than 25, so that's not going to work. And so now we have our solution. All we have to do is write our answer. So we've got -1/2 here. We've got 3 here, both solid dots, and the middle part is what's checked. So that's the part of the line we're going to draw. In set notation, we can write this all in one go. We've got -1/2 is less than or equal to x, which is less than or equal to 3. And in interval notation, we have the interval from -1/2 to 3, including our bounds, which is represented by a bracket. All right, let's do one final example to wrap up this section of notes and this unit. We have 5x squared equals 27x minus 10 as our related equation. We're going to pull everything over to the left-hand side. So that's going to give us -27x plus 10 equals 0. And now we need two numbers that multiply to give us 50 and add to give us -27. Those numbers are -2 and -25. So we'll do 5x squared minus 2x minus 25x plus 10 equals 0. Factoring by grouping, we can pull an x out, which leaves us with a 5x minus 2. We want a 5x minus 2 to come out over here as well. And the number we pull out to make that happen is going to be -5. And so we end up with 5x minus 2 times x minus 5 is equal to 0. So our x values are going to be either 2/5 or 5. So we pull out our test line. We've got 2/5 here. We've got 5 here. And now we're going to do what these points are. They're going to be solid since we have greater than or equal to. And now all we've got to do is our test values. So a number that's less than 2/5, well, let's go with 0. 5 times 0 squared is greater than or equal to 27 times 0 minus 10. So that gives us 0 is greater than or equal to -10. Well, that's true. And so this part of the graph is good. Now let's pick a number that's between 2/5 and 5. Well, how about 1? 1's easy enough to work with. So we've got 5 times 1 squared is greater than or equal to 27 times 1 minus 10. So we end up with 5 on the left-hand side is greater than or equal to 17 on the right-hand side. 5 is not greater than 17, so that doesn't work. And then our last test point, let's use 10. 5 times 10 squared is greater than or equal to 27 times 10 minus 10. So on the left-hand side, we get 500. It's greater than or equal to 260 on the right-hand side, and that's true. So now we have everything we need to write our final answer. So we've got 2/5 here. We've got 5 here. And we know that both of these are going to be solid. And the part of the graph that has the check marks are left of 2/5 and right of 5. So in set notation, we have x such that x is less than 2/5, or x is greater than 5, And actually, we have an equals to on both of those because we're including 2/5 and 5. And then interval notation, we're going from negative infinity to 2/5, union with 5 to infinity. And that would be our answer for this one. So, after quite a number of examples, you should be pretty familiar with how these problems work. And this is going to wrap up not only the section, but this unit. And we spent the last couple of units on quadratics. So, as we move on into Unit 4, we're going to be moving into functions that have higher powers than 2. And we'll be talking about cubic functions at the beginning of Unit 4. So you'll be expecting that in the next video.